I want to continue our discussion of forces. In this segment, I want to talk about Newton's second law. So Newton's second law is possibly the most important of the three laws, but together, the three of them form a complete description of motion. And as I've said, this was published in the Principia de Mathematica by Isaac Newton in 1687 for the first time. As far as we know, still works, so we're still teaching it. People still use this idea to build a building, or a car, or a rocket, or an airplane. They still use Newton's second law. So this is not baby physics, this is the real deal, people. Okay, Newton's first law says what an object will do if there's no net force acting on it. So if there's no net force acting on an object, it will just continue to do what it has been doing. If it was moving, it will move in a straight line at a constant speed. If it was at rest, it will continue in a state of being at rest. Newton's second law tells us, okay, what happens if there is a force on an object? Well, it will accelerate. And so Newton's second law is best described with mathematics. And it looks like this. A few things to point out. Force is a vector. Acceleration is a vector. Mass is not, right? Mass is a scalar. Therefore, the direction of the net force is the same as the direction of the acceleration. Because they're both vectors, and they're the only vectors on either side of that equal sign. They must have the same direction. Okay, the net force. What do I mean by the net force? Well, the net force is the sum total of all the forces acting on an object. The sum total of all the forces acting on an object. And I mean the vector sum. We have to be a little bit careful. It's not just the additive sum. It's the vector sum. And we've practiced adding vectors just a little bit. We'll come back to that in just a second. So this says that the acceleration of a mass, of an object, is directly proportional to the net force on it and inversely proportional to the mass of the object. And so, I think Newton's first law is a little bit tricky conceptually because a lot of us are stuck in this Aristotelian mindset. I think Newton's second law is pretty straightforward. Mathematically, it can get a little bit tricky, but I don't feel like conceptually students have too big of a problem with that. You push on something to make its velocity change. How hard do you have to push? Well, it kind of depends on how big the object is, right? A really big object, you got to push real hard. Tiny object, you got to push a little bit in order to change its motion. Now, I do think that one place where one common misunderstanding here is students think that the net force directly affects the velocity, and it just doesn't, right? So if I'm pushing harder on object A than I am on object B, it doesn't necessarily mean that object A is moving faster, right? It means, I don't know, we got to know what their mass is and stuff, but again, forces don't tell us about velocities, they tell us about changes in velocities, right? So forces are the cause, a change in velocity is the effect. We can think of Newton's second law as a cause and effect relationship. The force is the cause, the acceleration is an effect. How much effect do you get? Well, it depends on how much mass there is, right? A bigger mass, a smaller acceleration. That's Newton's second law. Again, I can ask you some tricky problems, but conceptually, it's just not that bad. The vector sum. What do I mean by the vector sum? Well, what I mean is you can't just add them all up straight away. The direction matters. And, sometimes I think it's nice to start with a super straightforward example. And here's one. Just to be sure we understand what net force means. Let's take a straightforward example. Let's say I've got this wagon right here, and we've got two kids, Timmy and Bobby, are both pulling on the wagon. Here's my wagon. And Timmy and Bobby could pull in a number of different directions. They've got some ropes hooked up with their wagon. They've been practicing all week. They're getting good at it, okay? So Timmy pulls right here with a force of 3 newtons, and Bobby pulls right here with a force of 4 newtons. Well, what is the F net here? Well, both forces are in the same direction. If we wanted to get super fancy about it, we could say, oh, well, to the right is positive, so these are 2 positive forces. What is F net here? Well, F net is 3 newtons plus 4 newtons is 7 newtons. Blowing your mind, I can tell already. Okay, how about, that's one way that Timmy and Bobby could pull. But what if Timmy pulled over here with 4 newtons, and I've been not careful about my drawing here, right? the length should be proportional to the magnitude. There we go. That's a better drawing. That's a better drawing. Okay. Timmy's pulling over there with 4 newtons, and Bobby pulling over there with 3 newtons. Is the total force still 7 newtons? It's not, because we've got to add them like vectors, right? And 4 newtons this way plus 3 newtons that way is definitely not 7 newtons. In fact, it is 1 newton. 1 newton in what direction? To the right. So both of these are to the right. Calling them positive is enough if we believe our coordinate system. Well, not the only ways Timmy and Bobby could pull, right? What if this was a top view right here? This is a top view of Timmy and Bobby's wagon. And now we've got Timmy pulling over yonder with 4 newtons. And Bobby pulls right there with a force of 3 newtons. Now what's the total force? Is it still 7? 1? Something different? It is something different. In this case, we need to make a triangle, right? Because these are at right angles. So in this case, we would have 4 newtons here, 3 newtons here, and there's my 3, 4, 5 triangle. So the resultant there is F net is 5 newtons. So for this situation, F net equals 5 newtons. So what is 3 newtons plus 2 newtons? Well, it depends on the direction. It could be 7, it could be 1, it could be 5, it could be something in between. So keep that in mind. That's what we mean by F net. There's a quick rundown of what Newton's second law is. Cause and effect. Force is the cause, acceleration is the effect. Velocity is not the effect. Change in velocity is the effect. Let's try a couple of quick clicker question examples. Okay, here's one. An object, when pushed with a net force F, has an acceleration of 2 meters per second squared. Now, twice the force is applied to an object that has 4 times the mass. What will its acceleration be? I'm going to pause the video, see if you can figure it out. I'm going to solve this kind of the longer way first, and then we'll see if there's maybe a little shortcut we could take. The way that we could write this is we could write this as A1 equals F over M. We're all in one direction, so we can just drop our vector sign. So this would be F1 over M1 equals A1. And then we could write A2, well, that's just F2 over M2. I haven't done anything too exciting yet. But now I can plug in what they tell us. Now they say twice the force is applied. So F2 then is 2 times F1 to a mass that has 4 times the mass. So then this is 4 times M2. Excuse me, M1. 4 times M1. All right, so twice the force, 4 times the mass, gives us 1/2 A1, which is 1 meter per second squared. Okay, so that's sort of the longer way to do it. And indeed, there it is. But you know what else you could do? And this is a good trick to know if you're going to take the MCAT or something like that, or if you're headed for a standardized test that might use some of this material. What you can do is you can just think of this as A equals F over M, plug in the change, and recognize that anything that doesn't change, we don't plug anything in for. We just plug in a 1. And then whatever we get out will be the factor by which the acceleration changed. So twice the force, 4 times the mass, that's 1/2. And so we recognize that that is the factor that our original acceleration changed by. 1/2 of 2 meters per second is 1 meter per second squared. Okay, so a couple of ways of thinking about the exact same problem. Let's do one more. A 40-car train travels along a straight track at 40 miles per hour. Let's add the caveat that that is a constant 40 miles per hour. A skier speeds up as she skis downhill. On which is the net force greater? The train, the skier, is it the same on both, or there's not enough information to tell? Why don't you pause the video, see if you can't figure this one. Well, let's look at this. The 40-car train is on a straight track at a constant speed of 40 miles per hour. Is the train accelerating? Nope. So, what is the net force on the train? 0. F net on the train is 0. Oh my gosh. But it's a train. It's huge. It's really heavy. Doesn't it require some force to keep it going? Well, it requires no net force to keep it going. So if we think about our train, steam train. There's probably some forces acting on it, isn't there? Yeah, there's probably some huge forces. There's probably some drag and some air resistance, right? There's probably something pushing it forward from the engine. We're going to talk a little bit more about that in the next segment. There's probably some weight pulling down on it. There's probably a normal force pushing up. All of those forces are huge because this train is very heavy. So all of those forces are huge. But guess what? They all cancel. So the normal force is exactly the same as the weight. The drag is exactly the same as whatever force is pushing this thing forward, which again we're going to identify in the next segment. So even though this train has huge forces on it, the vector sum of all of the forces is 0. And so on which is the net force greater? Well, the skier. Why? Because the skier is accelerating, the train is not. The skier has the greater net force. A little bit tricky, but again, Newton's second law tells us about changes in motion. If the motion of the freight car is not changing, aka it's not accelerating, then the net force on it is